Welcome back. In this segment, we're going to introduce a new proof technique called a combinatorial proof. This proof technique applies to theorems of the form A equals B, where A and B are two distinct algebraic formulas. Now, we already know techniques for proving these theorems. For example, equational reasoning could be used, where you start from one side of the equality and then you perform a sequence of rewriting steps until you reach the other side of the equality. Now here we're going to outline a different proof technique that is based on combinatorics, that is, counting problems. So the first step to prove this kind of theorem is to find a set, say, let's call it S, such that one or the other of these two formulas is clearly an answer to the question, how many elements are there in that set? So for example, if S is the set of all binary strings of length 10, and somehow you know the formula for that number, and it happens to be one of these two formulas, then you identify this counting problem as the counting problem to use in that proof. Now the second step is to prove that there is another way to count the number of elements in that same set, and that other way of counting it yield the other formula. Since a set only has one number of elements, and you computed it in two different ways, and these two different ways correspond to these two formulas, then the value of these two formulas must be equal, because it's equal to the number of elements in the set S. So to summarize the argument, by definition, a combinatorial proof of the identity A equals B uses the fact that the formulas A and B are two distinct formulas, or two different ways for counting the same number, namely the number of elements in a given set S. And the set S is one that you have to determine in the process of writing the proof. So, let's give an example of a combinatorial proof. In fact, let's use theorem 6, which we already proved in a previous segment. But the proof we gave earlier was not a combinatorial proof. It did not rely on counting the elements of a set. Instead, we used an algebraic proof, where we just used the definition of the combinations and other theorems, and then did some algebraic manipulations to go from one side to the other. Here instead, we're going to write a combinatorial proof. So theorem 6 is an identity or an equality where this is A and this is B. And the first step in a combinatorial proof is to identify a combinatorial problem or counting problem, where one of these two formulas or expressions is clearly the answer to the counting problem. So here we're going to choose this side of the equality because this is obviously the answer to a counting problem. Remember that by definition, CNR is the number of subsets of size R where the elements of the subset are taken from some set S of size N. So the first step of the proof, the combinatorial proof, is to identify a set whose elements we want to count. And here the set is the set of all subsets of size R. Now the second step in the proof is to find a different way of counting the number of elements in that same set, and hopefully end up with this formula as a result of the second approach. So what's a different way of counting the number of subsets of size R? Well, it turns out this number is also equal to the number of subsets of size n minus r when the subsets are taken from the same set S. So I want you to pause the video now and to make sure you understand why this number is equal to that number. So, did you figure it out? Should be pretty obvious, especially if you take an example. Now in general, let's consider the set S, with n elements in it. What happens when you form a subset of size R? Well, you pick out R elements, and let's say you take them out of S. How many elements are you left with? Well, you are left with n minus R elements. In other words, every time you pick a subset of S, the other elements, the one you did not pick, naturally form a subset of size n minus R, since the original set has size n. So what that means is that for every subset of size R corresponds one and exactly one subset of size n minus R. In other words, there's a one-to-one correspondence between the set of all subsets of size R and the set of all subsets of size n minus R. And because there's a one-to-one correspondence between the two sets, then they must have the same number of elements. And this is the justification for this equality. Now, it's pretty easy to wrap up the proof because by definition, the number of subsets of size n minus R where the elements of the subset are taken from a set S of size n is equal to Cn, n minus R. And this is exactly the expression B on the right-hand side of the equality. So this concludes our combinatorial proof of Theorem 6.